All right, so we are going to talk today about 7.3. Oops, let me get a little bit more ink going here. And 7.3 are maxima and minima, so max and mins, of functions of several variables. So just like we did in Calc 1, if you remember in Calc 1 when we kind of learned about this idea of the derivative and it being a rate of change, we also talked about how we can use it to find maximums and minimums, or to optimize, right? To find, we sometimes call it optimization, to optimize a function to see what is the maximum it can reach, what is the minimum. So we can do the same thing, and as you read through the book, you can kind of see, you know, if I think about a function now in 3 space as opposed to 2 space, this is my y, x, z up here, and I'm going to attempt, you guys will be nice to me, right? I guess I can't hear you, so I'm going to pretend, oh, I don't really like that. Let me undo that. I'm going to make kind of a function that clearly has a minimum, okay? And remember, this is 3-dimensional. Okay, and this minimum is going to occur, you know, we have this function of several variables, right? So when you plug in a and b, it spits out a z, or a height. And so the idea here is if you hold, again, the y constant and look at how x changes, and if I kind of you know, slice that, and this guy's going to be kind of parallel to the x-axis here, and if I graph and kind of look at what does this tangent line look like here, you can kind of see, now think of this as 3-dimensional, so this part right here really should be going kind of behind. If it could happen, it would go behind the computer screen kind of here. So I hope you can kind of visualize that. Also look in your book, they do a really nice job of that. And maybe I should have made this, so if I look at this tangent line, it's coming out here and then it's kind of going behind, right, the screen there. But if you can look at that, notice that the slope of this guy, so partial of f with respect to x, is 0. So this is a horizontal line that's kind of going above the xy plane. And then likewise, if I look at this the other way, if I set my x to be constant, and I'm going to look at my y, and I'm going to take a slice of this guy in the y direction, and I graph, you know, its tangent line here in the y direction, we can see that the partial of f with respect to y then at AB is also going to be 0. Okay, so I hope that makes sense. And you know, you wrote that down. There's a kind of a definition about that in your book, and so you should be writing those definitions down. You should be taking notes, just like this was a, you know, face-to-face class. But we found that if f of xy has a max or min, well, we should say relative, because these don't have to be an absolute, right? Relative max or min at AB, then what do we know? Then we know that the partial of f with respect to x at that point is 0, and the partial of f with respect to y at that point is also 0. Okay, so that's good. We would hope that would be true, because that's true for us in 2 dimensions, right? That the derivative is 0 at a maximum or at a minimum. So I hope that makes sense. So let's do, I don't have my notes out. Let's do a quick example of this. So I want to start off with a quick example. We'll just go right here. So let's say that the function f of xy, which in this case is going to be 2x plus 3y plus 9 minus x squared minus xy. This one's a little crazy. Minus y squared has a relative max. Okay, find where it occurs. All right, So if I want to find where the max occurs, well, I know from above here that if it has a relative max, then it must occur at a point where their derivative, the partials, are 0. So that's what I'm going to look for. So I'm going to take the partials. Remember, I'm not sure if I talked about this in the last section, but this is shorthand for the partial with respect to x. I'm not exactly sure why your book doesn't use it. But you're welcome to use this notation, and if you look online about partial derivatives or anything, you may see notation like this. F sub x, that just means the partial of f with respect to x. All right, so I'm going to go ahead and take that of this function of this guy right here, and I would get 2. The 3y goes away, the 9 goes away, get minus 2x, and then minus y, and everything else goes away. And I'm going to set this sucker equal to 0, of course. Now, just to make this look kind of pretty, I'm going to move this stuff around. I'm going to add the 2x and the 2 and the y over, and I'm going to leave the 2, and then I like having my variables on the left-hand side, but it doesn't matter. When I do f sub y here, I'm going to get 3 minus x minus 2y, set that equal to 0. Do the same thing. I'm going to do x plus 2y equals 3. And then what we really just have here is we have a system of equations with 2 unknowns. So this is basically from college algebra, and we all remember college algebra, I'm sure. And I hope you remember how to solve these. There are a couple ways you can do this. You could solve for this y right here, and then plug it in for this y right here and solve that equation. That would be sufficient. I like to do this method called elimination, where I'm going to basically multiply one of these equations by the opposite constant of one of the variables. So if you notice here, I have a 2x, so I want to get rid of the 2x, so I'm going to multiply everything by negative 2. Okay, and when I multiply everything by negative 2, so I'm going to rewrite this whole system here. So I'm going to rewrite it as 2x plus y equals 2, and on the bottom I get negative 2x minus 4y equals negative 6. And then what I can do, because remember, we're finding an x and a y that satisfies both of these equations at the same time. So I can actually add these guys together because we're assuming that both these equations are satisfied by the same thing. So if I simplify this, look at what we get. We get y equal to 4/3. And then how would I find x? Well, I'm going to take this equation right here because we're not really doing anything with y in that equation. And I'm going to plug it in to this equation. Okay, so what would we get here? Then I'd have 2x plus 4/3 equals 2. And I'll let you solve that. I won't waste your time solving an easy equation like that. What you end up getting is that x is 1/3. So what is our answer? Look at what this is asking. Find where it occurs. So the maximum, the relative max, occurs at the point, at the point 1/3, 4/3. All right, cool. That's pretty neat, huh? Those are kind of fun. I like doing this. Of course, that doesn't surprise you, right? That I like doing this. So I'm sure you have the question, as you should, that your question is, but Sarah, so that's great that it told me it was a max. What if it doesn't tell me it's a max? What if it tells me just to find the max or the min? So when you read through the book, and excuse me, for time's sake, I'm actually not going to write out too much of this. I'm going to do some examples for you because I keep doing that where I don't, I tell myself I'm just going to do examples and then I don't do it. So I'm just going to do an example. So you will need to look over the second derivative test. Excuse me. So look over the second derivative test. I'm not sure what page that's on. Let me grab my book really fast, and you should be copying that second derivative test into your notes, okay? So if you look on page 365, that shows the second derivative test, and we have this idea now where we have this new function, d of xy, which is second partial with respect to x times the second partial with respect to y minus second partial of f first with respect to y then with respect to x quantity squared. And so this mimics kind of the second derivative that we did in Calc 1. So if you remember with the second derivative test in Calc 1, right, if our second derivative was negative, we were concave down and we had a max, right? Concave down, we had a max. If f double primed was positive, we were concave up and that gave us a min. So when you look over that second derivative test, you'll notice when we plug the points in, the points where we're 0, into the f sub xx, we find, right, that if it's negative, we have a max, and if it's positive, we have a min, which would kind of make sense. So let's do an example. Now that you've written this all down in your notes, I'm going to let you do that. Whoops, I dropped my pen. So let's find all relative max and mins. So I'm just going to put relative extrema. That covers both. You know, mathematicians were lazy. Of the function. Well, we're lazy when we need to be, right? We're not going to be lazy when it comes to notation or making sure that our idea comes across very clearly. So let's find the relative extrema, max and mins, of x squared minus 2xy plus 4y squared. So first we need to find those a and b's where the partial derivative is 0. I'm going to call those critical points because that's what we called them in Calc 2, or in Calc 1, you are in Calc 2 now. So let's find the first derivative, partial derivative with respect to x. That's going to be 2x minus 2y. And this first partial derivative with respect to y is just going to be a negative 2x plus 8y. All right, so if we set those both equal to 0, let's set these both equal to 0, I notice right away that I can add these. If I add them right away, look at what happens. My 2x's cancel. 2x minus 2x is 0. Negative 2y plus 8y, that's 6y last time I checked. That equals 0. And then if we plug that in maybe up here, that tells me I have 2x minus 0, right? Oh, sorry, y equals 0. Equals 0, so that also says that x equals 0. So what's my critical point? It is going to be the point 0, 0. And then like the second derivative test said to do, we are going to take this point and plug it into that new function there. So to be able to plug it into this new function, I need to find these guys first, okay? So I'm going to find f sub xx. Okay, that means I'm going to go up to this function here, and I am going to take the derivative of it with respect to x, which would be 2. Then I'm going to find f sub y. So I go up here. The derivative of this function here with respect to y is 8. And then finally, f sub yx would be to take, again, this function here and take the derivative with respect to x. So that would just be negative 2. Okay, so what is my function d of xy? Well, this one's I wanted to do this one first because it's supposed to be easy, right? Because I just get constants, but it can be a little bit tricky too because of the constants. So again, look at what I'm doing here. I'm going to take the second derivative with respect to x, that's this guy here, okay? Then I'm going to take the second partial with respect to y, that's that guy there. And then what do? I subtract the second partial with respect to x and y, which in this case is negative 2, and I square it. So this is, what, 16 minus 4, because a negative 2 squared is a positive 4, so I get 12. All right, so now once you have that this second derivative function, this capital D function, I plug in my critical point. Okay, so I plug in my critical point, I get 12. This is kind of not very exciting because it's a constant, so it doesn't care. It doesn't care what the variables are. It will always be 12. Now remember, if it's greater than 0, then we plug it into f sub xx. That tells me if it's greater than 0, then I'm going to get a max or min. So then I'm going to plug in 0, 0 into f sub xx. But see, look at f sub xx, it's 2. So if it's 0, 0, it's just going to go to 2. This is greater than 0. What I like to think about, because you're going to need to know these, I will give you this function right here, but I'm not going to give you all of the stuff underneath that. You need to know that. So I'm going to have this is going to be greater than 0. So what does this give us? I kind of remember it from Calc 1. Greater than 0 means I'm concave up, and so we have a minimum. And then here is how I want you to write your answers. So this is why it's important to watch the video. This is not the minimum of the function. This is where it occurs, right? So we have a minimum at 0, 0. What is the actual minimum of the function? The actual minimum is how high that function goes, right? The actual minimum is going to be this function evaluated at 0, 0. So I would like you to state your answers like this. We have a relative minimum of, well, how do I find that? I evaluate the function at the point. If I evaluate this function at 0, 0, I get 0. So we have a relative minimum of 0. And where does it occur? It occurs at the point 0, 0. Okay? I hope that makes sense. Should it make sense? You should contact me if it doesn't make sense, as always, okay? All right, so let's do another example. How about, yeah, this will be a good one. These are a good time. So let me clear this out really quick. So again, find all relative extrema. Of the function, and here's my function. F of xy is going to be equal to x cubed minus y squared minus 3x plus, oh, I'm running out of room, 4y. Darn it. Let me write a little bit smaller here. 3x plus 4y. Sorry about that. Okay. So again, I need to find the critical points. The critical points occur where my partial derivatives are 0 at the same time. So if I take the partial with respect to x, I get 3x squared minus 3. The partial with respect to y is a negative 2y plus 4. So I like this example because it kind of shows you what happens when we get partials that don't have to do with the other variable. So remember, I want to find an x value and I want to find a y value that make my partials 0 when I plug them in. Well, if you notice, my f sub x only depends on x, f sub y only depends on y. So I just need to solve these. So this says that y must be 2, right? Subtract the 4, divide by negative 2. So I know y is going to be 2. Here, this says if I add the 3 and divide by 3, the x squared equals 1. Now, when you bring in a square root, please don't forget that you need to bring in a plus or minus. Take the plus or minus the square root of 1, right? Anytime you bring in a square root that was not there originally, you must bring in a plus or minus. So here are what our critical points are. Okay, our critical points, well, what do I have? I'm going to have two different points, of course. I'm going to have a point when x is negative 1, and I'm going to have a point when x is 1. Well, and then what is y going to be? It's just going to be 2 for both of those. And if you see, you sure could take these points and plug them into f of x, take this point, plug them into f of y, and you'll see you'll get 0 here because they each just depend on the x and the y. All right, so I need to find my capital D function. So I need f sub xx. If we look at that, that is 6x. F sub yy, that is going to be negative 2. And then f sub yx, that is 0. That's lovely. So here is what my second derivative function is going to give us. So remember, I take f sub xx times f sub yy, right? And that is going to be a negative 12x. And then I'm going to subtract this 0 right here, which is just 0, obviously. I used a different color there. I didn't like that. I'm a little OCD maybe. All right, so let's plug this in. So I'm going to plug in 1, 2 first. So if I plug in 1, 2, I'm just plugging in the x value because that's all we have. I get negative 12, and if you remember looking at the second derivative test, if I take that capital D, that derivative test function, and I get a negative value, that means that there is no extrema there, no max or min. And what we call this is a saddle point, okay? And saddle points are kind of interesting because what happens with the saddle point is it looks like it's a max from one direction, like if you look at it from one direction, and it looks like it's a min from the other direction. So I'm looking this up. They should have a graph of this for you. Yeah, so if you look on page 365 again. And if you look at the function on that page, it shows you kind of the saddle of it. It looks like a Pringle chip if you guys eat Pringles. I like Pringles. But if you look at one way, if you look at Y changing, it looks like a minimum possibly. And if you look when X changes, it looks like a max. So there's no extreme at that point. It is considered a saddle point because it looks like a saddle if you look at the graph of it. And we're going to plug in -1, 2. So this one's going to be interesting because this is 12, which is greater than 0. Okay, so then what's my next step from there? My next step is to evaluate f sub xx at -1, 2. So f sub xx is 6x. If I put in that -1, I get a -6, which is less than 0, right? Which I remember is concave down, so that is a max. You're going to need to know those criteria, okay? Again, I'll give you the function, but I'm not giving you the criteria all underneath it, those 4 steps. You need to know those. So look at what we have. We know we have a maximum. That's great. So let's see what we have then. I'm going to take f of, well, I know I have a maximum. I know where it occurs. Let's put in -1, 2 into my original function. So I'm going all the way back up here. So I'm going to take a -1 cubed minus 2 squared minus 3 times -1 plus 4 times 2. I can do this, right? So, well, I don't know what I did there. I get a -1 minus 4. -5 plus 3 is a -2 plus 8 is 6. Cool. So my final answer here is I have a relative max. This is how I want you to state these. We have a relative max of 6. Where does it occur? At the point -1, 2. And then what else do we have? We have a saddle point. There's an E on that. At 1, 2. This is how I want you to state your answers. Okay, I will take off if you don't do that. So I really hope you watch the video. If you hear me talking right now, you are watching it right now. So that's kind of a moot point. All right, I just want to do a couple more examples and then we'll call this good. Okay, so one more example of just doing these because these can be kind of tricky. So I'm getting a little lazy. Same thing, find all the relative extrema of something like this. How about 16xy minus x to the 4th minus 2y squared. So this is going to be kind of a long video today. But you get more for your money, right? You pay good money to be here or to take this class. So first partial with respect to x is 16y minus 4x cubed, right? Partial with respect to y, if I look at this, is 16x, right, minus 4y. And I'm going to set these equal to 0. Now, because I have this cube right here, I'm going to approach this a little bit differently. I'm going to do a method called substitution, where I take 4y and I'm solving for y here. So it looks like y is equal to 4x, okay? And now I'm going to take this y is equal to 4x, so this is my substitution method, and I'm going to plug that in for this y right here, okay? And, you know, I need some room here, so we'll go down here. So I would have 16 times 4x, and the reason I'm doing this is because I have a cube. So my elimination is not as easy. All right, so here's what we got, people. We get 64x minus 4x cubed equals 0. You must factor this to solve, okay? You can't divide everything by x. If you do that, what you're doing is you're assuming that x can't be 0. When we know if x is 0, it works, right? Oh, I did this in my class today. Okay, so I would get 16 minus x squared equals 0. And if you set each of these terms, this term and this term equal to 0, here's what I get for x. I get 0, 4, or -4, right? Because when I square root that 16, I need a plus or a minus. So I'm going to come back up here because I'm going to run out of room down here. Here are my critical points, okay? Well, when x is 0, what is y? 4 times 0, which is 0. When x is 4 4 times 4 is 16. And when x is negative 4, 4 times negative 4 is negative 16. All right, so I have 3 critical points to test. And what I need to do now is I need to find my second derivatives. So f sub xx is a negative 12x squared. F sub yy is negative 4. And f sub yx is 16. So that leaves me with the function capital D of xy equals these two multiplied together. That'd be 48x squared minus 16 squared, which is 256. All right, so let's start testing our critical points. Let's do 0. 0, 0 is always an easy one. If I plug in 0, 0, I get negative 256, which is less than 0, so we have a saddle point. So no extrema at that point. So no max or min. Okay, if I evaluate this function at 416, let's see what we get here. Well, all that matters is this x right here. So 4 squared is 16 minus 256, and I think you get something like 512 maybe? Let me check really quick. Yeah, 512, look at me. Okay, so that's greater than 0, so that tells us to keep going. So I evaluate f sub xx then at 416. Now look at what f sub xx is. It's negative 12x squared. So I would have negative 12 times 4 squared. I don't know what that is, but I know that's less than 0 because 4 squared is going to be positive. So we have a max. Okay, and then I get a negative 416. Everything's going to be the same here. So how do I know that? Because I'm squaring things. So when I square that 4, I'm not changing anything. So this will be 512 again, greater than 0. And then the same thing will happen with f sub xx, because when I put in a negative 4, remember you have to square first. So when I square negative 4, that's going to be positive. And then this negative right here will keep me negative. So again, I have a max. And then I'll let you finish up with writing. You know, you'll say we have a relative max of blah and it occurs at 416. Don't put blah. And I have a relative max of the other blah and it occurs at negative 416. Okay, so I hope that makes sense. All right, I want to do one more example of an application and then I will be done because I bet you're about done too. So let's do an application problem. Find the dimensions. Okay, of a rectangular box of volume 1,000 inches cubed. And I'll probably just set this up for you and let you finish it up because I think I'm probably losing you a little bit. For which the sum of the dimensions is minimized. So this one's a little tricky. A lot of times when I'm doing stuff like this and I don't know what's going on, well, I know what's going on, but if you're not sure what's going on, a lot of times what I like to state is I like to state what I want and then what is given. So what do I want? And if you took me last semester, this looks familiar to you. I want the minimum of, well, let's see what I'm going to do here. I have a box, rectangular box. This is looking more like a cube. Let's say I have a rectangular box, right? Okay, so here's my rectangular box. Ooh, I can even make this look pretty cool because I have an eraser. That's very exciting. So I'm going to label this box. I'm going to let's see. Sorry, I just got something caught in my throat and I was coughing. Excuse me. Okay, so it doesn't really matter how we label this. I'll let this side be X, I don't know, this side be Y, and we'll let this be Z. So look at what this says. What do I want? I want the dimensions, right, of the rectangular box for which the sum of the dimensions is minimized. So I want the minimum of the sum. So I'll just call it S for sum, doesn't matter. And I want the minimum of this function right here. Okay, but the problem is it's not a function of two variables. We need it to be a function of two variables. So I'm going to state my given here. What else has been given to us? There has to be a way, oh my goodness, I'm sorry, to relate these variables. And what they tell us is this information that the volume is 1,000 inches, cubic inches. So that's what I need to use, okay? So remember, volume of a box is just length times width times height. And that's what I have right here. So I'm given that x, y, z is 1,000. And that's how I'm going to relate the variables. So what I'm going to do with this is I'm going to solve this guy for z so that I can write my function s right here in terms of just x and y. So s now is a function of just x and y, which is good. And we can write this now then as x plus y plus, now instead of z, I'm going to put 1,000 over xy. So that's a little tricky, especially because I want to take the partial derivatives of it. So let's do x plus y. I'm going to rewrite this as 1,000 times xy to the negative 1. All right, so s sub x, that's the derivative of this function with respect to x. I would have 1 plus, well, I'm going to actually put minus because I'm going to do the chain rule here. I'm going to bring that negative down. I'm going to leave the inside. I'm going to take 1 away, and then I'm going to multiply this guy by the derivative of the inside with respect to x, which would be y. And I'm just going to rewrite this. 1,000, so I get 1,000 y all over xy squared, okay? And then likewise, s sub y, I would get 1 minus, it'd be the same idea here, 1,000, leave the inside, take 1 away, but now I need to multiply with the partial with respect to y, so the partial of xy with respect to y is going to be x. Excuse me. Man, I had a coughing fit right in the middle of this lecture. Okay, and we're setting each of these equal to 0. So, I was looking at this, and there are a couple ways that we can do this. So what I'm going to actually do is I'm going to do something called clearing fractions, and I'm going to multiply this whole side by xy squared, and this whole side also by xy squared. So the algebra on this can be a little bit tricky. Excuse me. Oh my goodness. All right. So if I do that, and I'll go ahead, xy squared is just x squared, y squared, then that cancels. I get minus 1,000 y equals 0, right? And then if I do the same thing over here, so I'm going to get the same idea here. I'm going to get x squared, y squared minus, now instead of 1,000x, I'm going to get, or 1,000y, I get 1,000x equals 0. Okay, so I'm just going to solve one of these for x or y. It shouldn't be too hard to do. So if I set these equal, now again, this algebra is getting kind of intense, but if I set this equal to 1,000y, okay, and then divide both sides by y. Now, why can I divide both sides by y? Because I know y is not 0. Because think of the context that we're in here. What is y? The y would be the side of the box. So that doesn't make sense for y to be 0. So in a case where it doesn't make sense for the variable to be 0, I can divide by the variable. And so I'm going to solve for y. And what does y equal then? 1,000x to the negative 2. And now what am I going to do with that? I'm going to plug it in here. Okay. I hope that makes sense. So this gets a little wild. So here I get x squared times, I'm going to square this guy. So I'm just going to write this as 1,000 squared because you're going to see stuff is going to cancel. And then I'm going to square that x to the negative 2, which will actually give me x to the 4th on the bottom. And I'm going to take this guy and move it over. So this will be 1,000x. And so if you simplify all this, I hope you would agree with me. I can simplify this, I can cancel. This would be a 2. Then I can move that x squared over and I would get x cubed And then on the left-hand side, I'm going to divide both sides by 1,000. So the 1,000 squared divided by 1,000, we'd just be left with 1,000. And so finally, oh my goodness, after all of that, what do we get? We get x to be 10. And if you take this and plug it into here, we see that y would be 10 also. Now I'm at almost 35 minutes, so I imagine I'm about losing you, but I hope that setting that up kind of makes sense. Now, to do the second derivative test of that would be tough, but look at what I've asked you to do. I've asked you to determine when it's going to be minimized. So do we really need to do the second derivative test? No, because this guy's only really going to have a minimum. If you think of the dimensions that might make it maximized, that would be a little bit different, but we only found 1 point, right? So our only point is 10, 10, and because it asked me to find the minimum, we know that the minimum must occur when x is 10, when y is 10, and then you can solve for z, and you will see that z is 10 as well. All right, I hope that made sense. Please let me know if you have any questions, and enjoy as you work on the homework.